Hi everyone, I'm Thomas from the Link Alliance of CityWell Link in Auckland. Today, I would like to present the deep underground mine cavern excavations in Auckland Central Business District. Here is the content today. First, I will introduce what is CityWell Link, then the Kawakahabi Station. We will also call it K-Row. In this project, we will use the building information modeling and the three-dimensional geological model. I will also give a brief description on the geology of Kawakahabi Station, then the numerical analysis for the design, and how we optimize. Finally is the tunnel construction and conclusion. Let's have a look what is CityWell Link. The Kawakahabi Station is between two lift stations, the Altier and Mount Eaton. It is a 32-meter deep mined underground twin-platform station. Also, it is the deepest station of the project. The entrances of the station are from both Mercury Lane and Belfast Square. It comprises two station shafts, one at Mercury Lane and one at the Belfast Square. At the beginning, we will also have the access shaft to get into the tunnel excavation first. Then the platform tunnels and 5 connection eddies. There are 2 platform tunnels called MC20 and MC30. It is mined using sequential excavation method, which are about 220 meters. The TPM is able to transit through both platform tunnels, first the MC30 and later MC20, from the south to the north. This is the building information model for the cable station. Both temporary and permanent supports have been included in the model, such as the TPM tunnel, the 2 platform tunnels, the temporary access shafts, and 2 permanent shafts. And why we need the building information model to help us? Because we want to achieve a single source of truth and long-term cost savings, to improve collaboration and reduce errors, to improve project delivery and collaboration, to improve safety and reduce risk in design and construction by crash analysis and 3D coordination of integrated disciplines. Also, to increase collaboration between different parties in link alliance and quick access to accurate information. The application of 3D geological model. Boreholes and corresponding testing data will be uploaded to the internet called soil cloud. You just can click a button and get the test data. That means you can access the database anytime, and it is a single source of truth. The 3D geological model was created by the client by using default works. Then the Link Alliance have developed this model and made a combination of geology and geological units. Then the law model also imported into the BIM. So you can easily see the relationship between the underground structures and the geology. It is quite useful in the presentation, in the discussion, analysis, and especially for our drawing preparation. Here is the geology of clay wall along MC30 platform tunnel. The tunnels are mainly embedded in the East Coast Base Formation called ECBF. It is a weathered, well-cemented, moderately strong sandstone. The thickness is various along the tunnel alignment. The bedding in this layer is mainly horizontal or subhorizontal. The unit drops in levels from the north to the south of the station. The tunnel excavation is mainly within massive US3 and EUG3. A slightly to unweathered weak to moderately strong ECBF materials. The unconfined compressive strength UCS is about 10 to 25 MPa with GSI 60 to 85. At the bottom and on the top of EU3 is the slightly to unweathered very weak ECBF called EU2. The UCS is about 1 to 3 MPa and GSI is 55 to 80. Based on the input from the BIM model and the 3D geological models, we have carried out the temporary support design by using the violent element analysis, such as the PASS 2D and 3D. Because we need to take into account the tunnel geometries, the geological conditions, socket stiffness development, temporary support requirements, the existing building loadings, and the shaft excavation. On the right-hand side, the figure showing the Bedford Square and the tunnel's excavations relationship. This is quite important to our project because the shaft excavation is concurrently with the tunnel excavation. Therefore, we need to know the relationship in terms of stress, loadings to each others. Of course, we also apply the analytical methods developed by past experience in the tunneling industry, such as the empirical ground stand-up time. Tunnel design has further optimized after obtaining more site data from the excavation, such as the mapping records. The initial design is limited by the joint information from the boreholes, due to spacing, drilling direction, and drill hole size. The optimization is to reflect the actual site conditions and to increase the construction efficiency. For example, on the right-hand side at the top, the flat 3D analysis at one of the platform tunnel junctions. The initial design is the split top heading excavation due to low rock height. However, this split top heading excavation make construction very difficult, and the temporary support very bulky. After getting the site data from the additional boreholes and the mapping records, we analyze the site conditions in the RS3 by incorporating the joints into it. After the analysis, we have confirmed that full top heading excavation can be carried out. Tunnel is excavated in a full reef top heading. Rafters and polypropylene fiber reinforced socket (PFRS) with the full thickness of the permanent support arch building up in layers. Excavator is used for all excavation under supported ground. All tunnels are constructed without any main entry under unsupported ground at any time. Here is the video showing the road header in action in the cable station. The current ground movements are kept under well control, and there are low adverse effects on the nearby structures. This is the end of my presentation. Thank you.